Here we go. All right. So halogenation regioselectivity. Question 10.12. Perfectly reasonable question. It just says predict the major product that's going to be obtained upon radical bromination of the following compound. So if we take this first compound and we treat it with bromine and light, you see that there's a few different types of protons in here, right? We have, this type of proton here. That's a secondary carbon-hydrogen bond. That's on a secondary carbon. If you look at this one here, for example, this one or this one, these are on primary carbons. But there's one carbon-hydrogen bond that's on a tertiary carbon. And if we abstract this one that I have highlighted in green, that's going to produce the most stable radical that could be produced. And we know that bromination is very selective to produce the most stable radical as an intermediate. So we could draw that intermediate just for fun. It's going to look like this. And I'll put it in square brackets just to denote that it's an intermediate. After this, we do the halogen abstraction. And then we end up with the product, which is going to have the bromine installed at the tertiary carbon. We use the exact same rationale for the next problem, right? I'm going to go over this one a little faster. Hopefully you can see that in this one, there is only one hydrogen that is attached to a tertiary carbon. And so that is the one that is going to get abstracted, right? After the bromine radical is formed, we do the hydrogen abstraction. Then the radical is going to react with bromine, Br2, to do a halogen abstraction. And we're going to end up substituting that hydrogen for a bromine. So we're going to end up with a molecule that looks like this one right here. And again, you can see the synthetic utility of this reaction, because if you were to take this compound, for example, and you were to treat it with Cl2 and light, you would end up with chlorination not only there, but here and here and here and here and here. You'd end up with a whole holy host of products, which isn't very useful when it comes to trying to develop new molecules. Well, what about this kind of radical intermediate? Remember that in the last lecture, we talked about the fact that the carbon radical is sp2 hybridized, and we can regard it as being trigonal planar. It has a trigonal planar molecular geometry. So what's the consequence of that when we're dealing with stereochemistry? Let's say we're doing the chlorination of butane, and again, we know that chlorination is not as regioselective, not nearly as regioselective. So we're going to get chlorination at this position, right? The methylenes and also the methyl. Anyhow, so with respect to the 2-chlorobutane that's formed here in this reaction, if we draw the intermediate, right, the intermediate radical that's formed, and I'll just pencil it in here. Let me draw it the way that they have it just to be consistent. Anyhow, here's that secondary radical that upon halogen abstraction is going to produce this compound. Well, we know, again, and I'm repeating myself, that this carbon is trigonal, right? It can be regarded as being trigonal planar. And so when the halogen abstraction occurs, it can occur from either face of the molecule, and thus we're going to end up with a racemic mixture, right? This compound here is going to be isolated as a mixture of R and S. And racemic mixture means a 50-50 mixture of R and S. So again, you see that, it's not a stereoselective reaction, right? We end up with a mixture of enantiomers. The next slide is nothing more than rehashing the molecular geometry of the carbon radical, which again, you can regard as either being trigonal planar or a rapidly inverting shallow pyramid. But either way, we're going to assume that it is planar, and that therefore the halogen abstraction can occur on either face of the molecule with equal probability. And that's why we're going to end up with a 50-50 racemic mixture. Again, just rehashing the concept right here. We take the chlorine, we end up with that racemic mixture of the 2-chlorobutane intermediates. We have the S isomer here, and we have the R stereoisomer there, and we also end up with 1-chlorobutane. Right? Again, the intermediate that produced the racemic mixture is going to be the secondary radical, right? And then the halogen abstraction can occur from either face of the molecule. And then the intermediate that's going to produce the 1-chlorobutane would be the primary radical, like that. Okay, so you have to understand that a radical is trigonal planar, and therefore when we can produce a stereocenter, we will, and we will produce a 50-50 mixture. Let's take a look at another example here. It says the halogenation of S3-methylhexane. So this is S3-methylhexane right here. In the halogenation of this molecule, the chirality center is the most reactive carbon in the molecule. But again, what's going to happen here when we do this? We're going to destroy the chirality center when we do the reaction, right? Because after we form the bromine radical, the initiation, the next step in the propagation, or the first step in the propagation, is the hydrogen abstraction. That's going to end up forming this intermediate, okay? And you can see that the chirality is destroyed, right? This is not a chiral molecule because this is trigonal planar. And then after the halogen abstraction occurs, we end up with a 50-50 mixture. We end up with a racemic mixture. Now, the chirality center is at that tertiary carbon. It's got the weakest carbon-hydrogen bond, weaker than the secondary and primary carbon. So again, bromination, here we don't end up with as many products, but we still end up with a racemic mixture, right? It's more regioselective than chlorination in that we only get bromination at this carbon. However, it is not stereoselective because the intermediate is a trigonal planar carbon radical. Well, with that in mind, let's take a look at some halogenation reactions wherein we have to consider stereochemistry. So it says predict the stereochemical outcome of radical bromination for the following alkenes, or sorry, alkenes rather. I got alkenes on the brain, right? Anyhow, so if we want to brominate this alkane, we've got bromine, and let's say we're going to treat it with bromine and light. We get a big light bulb and we shine it on the molecule. Well, hopefully by now you can see that the weakest carbon-hydrogen bond in the molecule is going to be this carbon-hydrogen bond right here, because this carbon is a tertiary carbon. So we're going to form an intermediate radical. I'm going to take the time to draw that intermediate radical. But what happens to our stereochemistry, right? We start out with a stereocenter in our starting material, and then we end up with a molecule that has no stereocenter, or I should say an intermediate that has no stereocenter. So then what happens in our last step? When the halogen abstraction occurs, and I'm just going to draw the mechanism because it's always good to practice your mechanisms, right? We have the carbon-bromine bond, oops, like that, being formed. Anyhow, and we end up with our brominated compound, okay? And we can draw, you know, let's say we put the bromine going down like this and the methyl group going up like that. Well, not only are we going to isolate this compound, but we're also going to isolate its enantiomer, right? If you flip the stereocenter here, we're also going to isolate that compound. Now, I know I'm rehashing this for probably the 10th time this morning, but whatever, it's Friday. You know, Rebecca Black is celebrating somewhere, so we're going to celebrate the fact that this is, again, trigonal, not TIG, trigonal planar, and thus the bromination can occur from either face of the molecule. So we end up with a mixture of enantiomers here. So we'll say racemic mixture, okay? Racemic mixture. Well, in this molecule, we've got two chiral centers, don't we? We have a chiral center here, and we have another chiral center here. Hopefully, again, by now you can identify the weakest carbon-hydrogen bond as being this one right here, because this carbon is tertiary. Let's draw the radical intermediate just to get some practice. So again, we treat that with bromine and light, and we produce this intermediate. This stereocenter is intact. Nothing changed about that stereocenter. Not affected in any way, but we destroyed this stereocenter here. So there's our intermediate. Now, after the halogen abstraction, we're going to isolate this compound where, again, this stereocenter remains unchanged. So we'll put that in. Then we're going to have the methyl group going up like this, the bromine coming down like that on my dash. And then I'm also going to isolate, I need to move this up. I'm also going to isolate this compound. There's that terbutyl group. There's my methyl group going down. I have my bromine going up like this and my methyl group coming down like this. Could anybody tell me what the relationship between these two compounds is, right? Going back to chapter 5 here. What would the relationship between these two compounds be? What kind of stereoisomers are these? Yeah, exactly. Thanks, Chris. They're diastereomers, right? This is a pair of diastereomers. Diastereomers. Okay, so here we end up with a pair of diastereomers. Now, something that is mentioned in the book, I don't think I'd ever ask you about it, but I thought but it is interesting to share it with you because it is in our book. It's the fact that you know how when we get a racemic mixture like we did here, we just say, okay, it's racemic. It's a 50-50 mixture. Well, if you look at this intermediate here, since it has a chiral center over here, the halogen abstraction isn't going to occur exactly with 50-50 probability. It's not going to be equal probability for each face of the molecule. The reason why is because the tert-butyl group is coming out towards us and the methyl group is going in back. And so this is a chiral intermediate, right? There is a stereocenter in the intermediate. And since the top face of the molecule here is going to be more hindered by that big tert-butyl group, the bromination is probably going to occur on the back face of the molecule more. So when you form a mixture of diastereomers, sorry about that. But gun, give up. Just let me. When you form a mixture of diastereomers, that's why we don't just say, oh, knee-jerk reaction, we'll just call it a 50-50 mixture, because it's probably not. Give me a thumbs up if that concept makes some sense to you. Just the whole idea that the mixture of diastereomers probably wouldn't be a 50-50 mixture. Okay, cool. Can you guys still see my screen? I think you can, but I want to be 100% sure. Can everybody still see my screen? Okay, thanks, Moira. Good. All right, and something else that's cool about the whole concept of diastereomers, and I promise I'll stop now talking about mixtures of diastereomers, but you can actually harness the power of this, right? Let's say you're doing a chiral synthesis. You can actually harness the power of the fact that you've got a stereocenter here, and you can, promote the bromination maybe more on one side than another. So anyhow, that's kind of beyond the scope of our course, the whole concept of using a stereocenter to our synthetic, advantage, but still kind of an interesting thing to think about. All right, well, let's take a look at what's called allylic halogenation. I told you there aren't many reactions that we learn in this chapter, not many new reactions, but this section does deal with a new reaction. And if you're thinking, well, halogenation, I already know halogenation just with bromine and light or bromine and heat. Yeah, I can do that. But what if you want to do an allylic halogenation? Why would you want to do that? Or why can you do an allylic halogenation? If you look at this molecule here, you see that you have three distinct types of protons that are highlighted in red, blue, and green. The one that's in green, right, this is simply a carbon-hydrogen bond on a secondary carbon. So this is on a secondary carbon. The one in blue is allylic, isn't it? This is allylic, and the one, we could say it's secondary allylic. And the next one, this is vinylic, okay? So the vinylic one is definitely going to have the strongest bond. We're not going to break a vinylic carbon-hydrogen bond to form a vinylic radical, right? That is really unfavored. But if we compare these two, if we were to do the hydrogen abstraction here, we end up with an intermediate that is not resonance stabilized. However, if we were to produce a radical from this carbon-hydrogen bond being homolytically cleaved, we would end up with a resonance stabilized intermediate. And so the allylic bond is the weakest. And so if we treat this with bromine, which one of these bonds is going to be most selectively broken, or which hydrogen will be preferentially abstracted? It's the one in blue. Okay, it's the one in blue. But the thing is, there's a problem with that, because if I just take this molecule and I just treat it with our plain old Br2 in light conditions, well, you guys know that bromine can react with an alkene, can't it? All right, so this is where we run into an issue, and that's why we have to learn a new set of reaction conditions. Let me show you what you're going to do here. says here, when you abstract that hydrogen, that allylic hydrogen, you get that resonance stabilized allylic radical. No big surprise there. So if we brominate an alkene, and again, if we take this molecule, cyclohexene, and we just treat it with bromine, we can get allylic bromination. However, the problem is that the addition of bromine to the alkene is a competing reaction. Now, I didn't really give myself enough reaction to do this, but since you're in bromine, you're also going to get a whole bunch of this, right? You're going to get a bunch of this, the trans 1,2-dibromo cyclohexene plus, it's an enantiomer, and that is not what we want. We want to do the allylic bromination. So there is a way around that. And the way that we work around that is we use a brand new reagent called NBS, which stands for Nbromo succinamide. So NBS or Nbromo succinamide, which affects an allylic halogenation or an allylic bromination since it's Nbromo succinamide. Anyhow, so let's see what it says here. It says to avoid that competing alkene addition, right, forming of the trans dihalo product, the way that we avoid that is to use NBS as a source of bromine radicals instead of using Br2, just molecular bromine. Now, how does this work? Now, the book doesn't cover the entire mechanism from soup to nuts. It covers parts of the mechanism. So the first step is you take that NBS, which is a really fun compound to work with because it's a white crystalline solid. It does degrade slowly over time because the nitrogen-bromine bond is so weak. And in fact, if you ever have a sample of NBS, you usually have to recrystallize it right before you use it. So everybody who's hearing the sound of my voice has done a recrystallization at some point in the organic chemistry lab. So you know the technique of recrystallization. So you actually recrystallize this reagent very quickly, and it can be recrystallized from water. Anyhow, so you take that NBS and you treat that with light, and that produces a bromine radical, right? But the idea is that when we use Nbromo succinamide, we keep the concentration of hydrogen bromide and of molecular bromine very low so that we don't get competing reactions. So in essence, after we produce that bromine radical from the NBS, we do a hydrogen abstraction. Once we've done the hydrogen abstraction, the HBr that's produced, this HBr here, reacts with NBS to form bromine. Now, this mechanism is not covered in our book, okay? And this mechanism right here is an ionic mechanism. It is not a radical mechanism, okay? I'll just tell you quickly that HBr reacts with NBS. You end up forming what's called succinamide and bromine, Br2 left over. But think about it. Even if you're like, I'm not 100% sure what you're saying, Mr. Dion, watch. Just back up here for a second. And let's think about this very carefully. If I only treat my allylic molecule, if I have 1 mole of my allylic, carbon-hydrogen bond, and if I throw in 1 mole of NBS, right, I'm going to form 1 mole, or let's say some bromine radicals and HBr, okay? But the only time I'm going to have bromine in my reaction mixture is when the HBr reacts with NBS to produce it. So it's really going to limit the amount of Br2 that's in the reaction, and the only time you're going to have it is when you have the allylic radical present. So you get the halogen abstraction occurring, and there you have it. That's allylic bromination. Now, I'm probably not going to ask you a ton about this mechanism, but again, like I always tell you, the more that you understand about a mechanism, the more fun organic chemistry becomes, the more rewarding it gets. And so what are you responsible for knowing? Really, what you're going to be quizzed on is this, is that if you take NBS and you take your allylic carbon-hydrogen bond, or your compound that has an allylic carbon-hydrogen bond, when you treat that with NBS and light, you get the allylic bromination, but you can end up with a mixture of isomeric products if you can produce a resonance stabilized, if the intermediate has a resonance contributor that is different from the radical that you're starting out with. So that's just a complicated way of saying you take your allylic carbon-hydrogen bond, right? You do the hydrogen abstraction, you form the radical. If you have these two resonance structures and they're different, well, then once you do the halogen abstraction, you're going to end up with a mixture of products, okay? So that's all there is really to it. What you really need to know is that you take NBS and light, you have an allylic carbon-hydrogen bond, and you do a bromination. So let's practice. This is question 10.16. If we take B, the molecule that's in B, and we treat this with Nbromo succinamide and light, well, how many types of allylic protons are there in this molecule? The good news is that we only have one type. It's this one here. If we draw the intermediate that's produced, we're going to end up with something that looks like this. We have this primary allylic radical, like that. Okay, we have this guy like this and this. Okay, is this resonance stabilized? The answer is yeah, absolutely it is, right? If we draw the resonance contributor, it's going to look something like this. Let's draw it out. If we draw that out, I'm just going to paste that. If I delete these and delete that and delete this, I'm going to end up with this radical. Can anybody tell me what the relationship between these two radicals is? And it's not a trick question. What's the relationship between those two radicals? Are they isomers? Are they stereoisomers? Could anybody tell me what the relationship between these is? Okay. The relationship between these two is that they're identical, the exact same thing, right? Because we have free rotation around, we have free rotation around this carbon-carbon bond. And so these two molecules are the exact same thing. So we only end up with one radical intermediate, right? So we can just delete this one here. We'll just erase that. And then this is our only intermediate that's produced. We can delete that. And the product that we're going to get, it's going to look something like this. And I can erase this, this. And we're going to have our bromine installed there. So we only end up with one product in this case. Now in the next case, things get a little spicier. We've got NBS and light. We've got two allylic carbon-hydrogen bonds, but they're both identical, right? Because there's a plane of symmetry, or an axis of rotational symmetry, I should say, down the molecule, right? If you rotate it around this point 180 degrees, you end up with the same thing. So these two carbon-hydrogen bonds that I have highlighted in green are identical. I'm just going to erase the one on the left, and we'll just do the hydrogen abstraction on the one on the right. Again, they're identical. So if I draw the intermediate that's produced, it's going to look like this, okay? I have that tertiary allylic radical, but this is resonance stabilized. So let's draw the resonance contributor, draw the resonance arrows, and then what I'm going to end up with is something that looks like this. Or I have the radical over here, right? These are the two resonance contributors. So I can do the halogen abstraction on either of these. If I do it on the one that's on the left, I'm going to end up with this compound where I have the bromine installed here. And if I do it on the one on the right, I'm going to end up with this compound here. Like this. Okay. But the thing is that this one here has a chiral center. Right? There's no chiral center in this one. That's not a chiral center. But this is a chiral center, the one that I have the red star by. And so this is going to give you a pair of enantiomers. Enantiomers. Could anybody guess which one of these would be formed in a greater yield? Would it be the one in the blue box or the one in the green box? Which one of these would be formed in greater yield? The enantiomers or the single compound in the blue box? Which one do you think would be isolated in a higher yield? Yeah, exactly. Thanks, Patrick. It's the one in the blue box, right? We're going to get that one in a greater yield. Greater yield. because this is the most stable radical, right? This one is tertiary allylic, and this one here is secondary allylic. So tertiary allylic wins over secondary allylic. So I would say that the one in the blue box would be isolated in a greater yield, and then you have a mixture of enantiomers. All right, there you go. So that covers allylic halogenation. One quick note of just interest, I'll tell you, is for any of my students who are interested in writing the MCAT exam, the MCAT exam, allylic bromination is one of those reactions they love to bring up. It's just kind of a dark horse. It's a bit of a chestnut that, you don't look at a ton after this chapter. It does come up from time to time, but not nearly as much as, addition of bromine across a pi bond, right, that we looked at in the alkenes chapter. It does come up from time to time, but it's one of those things that they love to bring up in the MCAT. It's like, what do they like to ask you about general chemistry too? Electrochemistry. It's the last chapter you look at or something. Usually at the end of the semester, you don't care, you're tired. The professor's teaching faster because he wants to finish everything. Anyhow, let's talk about radical addition of HBr. This is a reaction that we learned way back in chapter 9. Remember this one? Yeah. Remember we talked about if we have an asymmetrical alkene and we treat it with just some HBr, we get the Markovnikov addition, right? The rich get richer. This is the carbon that's richer in hydrogen, so it's the one that takes the hydrogen. The other one takes the bromine. Markovnikov addition, walla walla bing bang, right? Well, what if we take HBr and we throw in some peroxides? Then we get Antimarkovnikov addition. But if you remember that back in chapter 9, I didn't go over the mechanism of Antimarkovnikov addition at all, and I told you it would be covered in chapter 10. I don't like to promise things, but I promise if you pay attention to the mechanism for Antimarkovnikov addition, which proceeds via radical intermediates, you are going to understand it, okay? It makes a lot of sense. So it's a radical mechanism, different mechanism and a different selectivity. So let's see how it works. So what do? Well, you start out by throwing in peroxides, right? What are your reaction conditions? You've got HBr and peroxides, ROOR. That's the same thing as RO, right? And you put in the lone pairs. Oxygen has 2 bonds and 2 lone pairs, right? So we have that peroxide, which is our radical initiator, okay? So you heat it up, you break it apart, and you end up with some radicals. Then that that radical is going to react with the HBr to form a bromine radical. Okay, so that's the start, right? That's the initiation of the whole process. That's kicking everything off. First, you create a radical, right? When you have no radical, then the radical reacts with some HBr and you form a bromine radical. Now that you've got a bromine radical, you're ready, man. The world is your oyster. So here's how the Antimarkovnikov addition works. And this is why we get Antimarkovnikov addition. Watch carefully. If we have our pi bond and we have our radical, right, we're going to form a radical intermediate by the addition of a radical to a pi bond, right? This is one of the mechanisms that we looked at during the last class. If we add the radical on the least hindered carbon, we're going to end up producing this intermediate, which would produce a tertiary radical, right? You see the bromine is being added to the least hindered carbon, which is the opposite of what happens in Markovnikov addition, right? This is anti-Markovnikov addition. This is the anti-Markovnikov addition of bromine, right? You get, look, a tertiary radical. Okay, now I'm going to erase some of this. Okay, I'm going to erase this and this and this. Now, what if we added the bromine to this carbon, right? The other carbon, the other vinylic carbon. Well, in that case, what's going to happen? I'll draw a fishhook like this, another one like this, and we're going to end up with this, which produces a secondary radical. Give me a break. Which one of those is more stable? A tertiary is much more stable than a secondary. And this is the answer, my friends. That's all there is to it. There wasn't a long explanation, was there? All it is the bromine is going to add to the double bond so that it produces the most stable radical. That's it. That's why you get anti-Markovnikov addition. Once you've formed the more stable radical, you do a hydrogen abstraction, done. Reaction is over. That's it. That's the whole dang explanation right there. Give me a thumbs up if you follow me on that rationale. It's just about the bromine adding in such a way that it produces the most stable radical. And that, my friends, is why you have anti-Markovnikov addition. Right? If you think about Markovnikov addition, what was the first step in Markovnikov addition? It was the protonation, right? The proton transfer to form the most stable carbocation. So we added the H first, right? Now we're adding the bromine first. All right. Anyhow, so there you go. The bromine adds to the less substituted carbon. You end up producing the most stable radical. You do the hydrogen abstraction in the next step. So these are just your propagation steps. And then the termination, any two radicals, I don't give a crap what they are here. I just have two bromine radicals coming together. There you go, man. And again, the termination is usually students' favorite step because any two radicals that you've got in the soup, if they come together, that counts as a good answer. Now, next slide. It says here, the addition thermodynamics. So if we're doing the anti-Markovnikov addition of HBr across a double bond, right? We said that we could do this reaction, right? HBr, and peroxides. However, we said that we're not going to do it with HCl and peroxides. That's not going to happen. Not going to do it. Okay. And HI and peroxides, also not going to happen. For Chemistry 3101, that is all you need to know. Okay. You just need to know that HBr and peroxides is going to work and the other ones aren't going to work. In our book, he goes through an entire treatment of the thermodynamic considerations for the propagation steps, meaning the addition, right? So this is step one, okay, of the propagation steps is the addition to the pi bond, and step two, which is the hydrogen abstraction. So what he does in the book is he evaluates the first step, and I'm just going to show you quickly, and I'm not going to go over it, okay? He looks at the first step and the second step, and he compares HCl, HBr, and HI, okay, all three of them. And then what he does is he evaluates the delta G for each step, okay? So the delta G for the radical addition for HCl addition is negative, right? So that would be an exergonic process. So you think, okay, maybe it's going to be spontaneous. However, the delta G of the second step is positive. It's endergonic, and that's why HCl radical addition doesn't work. If we look at HI, the first step is endergonic, and so the reaction isn't going to work. The second step is exergonic, but since the first one is endergonic, it doesn't work. So this explains why HCl radical addition and HI radical addition don't work. However, the first and second steps for HBr and peroxides, both the addition and the hydrogen abstraction, you can see that they are both exothermic, right? So it results at low temperature in giving you a delta G that is negative, okay, for both steps, and therefore the reaction is spontaneous. So there you go. That's my treatment in a nutshell, and that is really all you need to know. That both steps for the HBr process are exothermic, and again, at low temperature, it's going to give you a negative delta G in both cases, okay? There you go. That's my whole treatment. He goes into more detail in the book, but really that's all you need to know. And organic chemistry students really just need to know the most important things, right? The things you're going to be asked, because let's face it, there's enough content in this class to begin with. Well, what about the stereochemistry of this kind of anti-Markovnikov addition, right? You guys know that we start out with our bromine radical, right? And we have addition to the pi bond, okay? So we're going to end up forming that radical intermediate. Then we do the hydrogen abstraction. Well, if the substrate isn't chiral, then you're going to get a 50-50 mixture, right? You're going to get a racemic mixture. And that's what you would obtain here. We have a chiral center here, so you'd end up with a 50-50 mixture. But if the starting material has a stereocenter, then you're going to get a mixture of diastereomers. Don't worry about the percentage of, maybe I'll get more of this, maybe there'll be less of that one. Don't worry about that at all. That would be more of an advanced organic chemistry topic, where, maybe you look at that in detail for a couple of reactions or something. So with all that information in mind, let's try some practice here. And these are questions that you would have been able to answer weeks ago, right? Because we looked at the Antimarkovnikov addition across a double bond. But now we're going to take stereochemistry into account. And I think the best way to do this is to draw the radical intermediate. I'm really obsessed with drawing mechanisms and intermediates if it's going to help me understand what's going on. Sometimes people draw a bromine radical like this. They leave out the 3 pairs of electrons and they just leave the 1 unpaired electron like this. So let's give that a shot. We add the bromine to the less hindered carbon, right, to produce Antimarkovnikov regioselectivity. Let's draw the intermediate that's formed. We have our bromine here. We have our tertiary radical like that. Well, now we're going to do the hydrogen abstraction. In the next step is going to be the H abstraction. But remember, this is trigonal planar. And so the hydrogen abstraction can occur from either face of the molecule. That's going to produce a mixture of enantiomers, right? It's going to produce a 50-50 mixture. So we're going to have the methyl group pointing up, and we're also going to have that methyl group going back behind the page like a Sioux, okay? Because again, the hydrogen is going to add from either face of the molecule. So here we're going to end up with a racemic mixture. Let's try the same exercise for the next one. If we draw our bromine radical, like this. Let's draw some curved arrows. So we have a fish hook here, we have another one here, and another one like this. We end up with this intermediate, okay, like this. And I have a question for you guys. Is this going to produce a compound with a chiral center or a compound with no chiral center after the hydrogen abstraction? Yes, chiral center, no chiral center. We're going to end up with no chiral center, right? We end up doing the hydrogen abstraction, and we end up with this compound, right? And this is not a chiral center. So we end up with just one molecule like that. Thanks, Josh. Great. All right. There we go. So that brings us to the end of the new reactions and new mechanisms and new, regioselectivity and stereochemical considerations that we have to take into account. And the last section that we're going to look at in this chapter is section 10.13, which is just the synthetic utility of halogenation. The only time that chlorination is going to be really useful for a synthetic organic chemist is when she or he is starting with some kind of substrate that is perfectly symmetrical, right? If you have a highly symmetrical substrate like cyclohexane and you treat it with chlorine, well, there's only one type of carbon-hydrogen bond in the whole molecule. So in this case, chlorination would work. Bromination is slower, but it's more selective. So here in this molecule below, not only do we have, the tertiary carbon hydrogen, we also have primary carbon hydrogens, right? There's some here, there's 3 here, right? There's some there. We have the secondary carbon hydrogens, but you know that this is going to be the weakest bond. And so bromination is selective for the weakest carbon hydrogen bonds. And so this is going to be really synthetically useful for us. So bromination is going to be used a heck of a lot more for my students in Chemistry 3101 because we usually deal with molecules that aren't going to be highly symmetrical. Are we going to look at highly symmetrical molecules? Of course. Yeah, from time to time we do. But I would say more often than not, we look at ones that are not highly symmetrical. So with that in mind, here is what you can do. If you start with an alkane, right, up until now, the only thing that you knew how to do with an alkane is burn it, right, is to treat it with oxygen and set a match to it, right, and you produce carbon dioxide and water. So a combustion reaction learned in General Chemistry 1. But now you can take just a plain old alkane that you got maybe from the refinement of, crude oil, so like methyl cyclohexane like this. You can treat it with bromine and you make this 1-bromo, 1-methyl cyclohexane. Now what can you do with a halogen? Right, an alkyl halide. You could do a substitution reaction like an SN1 reaction. Maybe you could treat it with water and you could make a alcohol. then you could do an elimination. You could do an E2 elimination with a hindered base or a non-hindered base. Here they're using an unhindered base like sodium methoxide, but you could also use a hindered base like T-butoxide, and you could make, methylene cyclohexene, this molecule. And then once you've got an alkene, holy smokes, right? The world is really your oyster then. Does anybody know what this is here? What I have drawn here? Not drawn, that's a copy and paste, isn't it? But does anybody know what that is supposed to mean? Yeah, that's right, Patrick. It's Pandora's box, right? So you open up Pandora's box of possibilities. The sky is the limit for you now. You're really blowing things up. You're starting with just a plain old alkane, right? Think about the first chapters you learned. You learned how to name alkanes, and now you're taking an alkane and you can convert it into all kinds of different compounds, right? What can we do with an alkene? We can do dihydroxylation. We can do hydroxylation. We can do halohydrin formation. We can do halogenation. There's so many different things you can do with an alkene, and that's the way that you have to think as an organic chemist. I worked in a program a number of years ago, and I worked at Boehringer Ingelheim. By the way, the Boehringer family is supposedly one of the top 10 richest or wealthiest families on the planet Earth. Anyhow, they didn't give me any of their, anything from their coffers. But when I was working for them, I worked with a guy who had a lot more experience than me, and we were trying to come up with some new potential drugs. So basically, making some new molecules that we were going to test in an assay. And he said, "You go to your office and come up with some ideas. I'll go to my office and come up with some ideas. And then when we come back, we'll meet, and then we'll see what we got here, and then we'll kind of triage it and go from there." So I went to my office and I came up with a couple of things, and then he came out and he had like a notepad with 5 or 6 pages full, and he said, "Okay, is this all you have?" And I said, "Yeah, this is what I wrote down." He's like, "Okay," and he said, "I have a question for you, Dan." He's like, "If somebody gives you lemons, like let's say you have a friend who has a lemon tree, and they have a big lemon yield, and they give you a big bushel of lemons, or I don't know what lemons are measured in, but they give you a whole bunch of lemons. What would you do with those lemons?" And I said, "I don't know, make a lemon pie." He said, yeah, that sounds good. A lemon pie sounds delicious. But he said, the way an organic chemist has to think is not, I'm not just going to take this and make a lemon pie. I'm going to make lemon cookies, a lemon pie, lemon bars, lemon squares, lemon schnapps, a lemon drink. I'm going to make some kind of lemon drizzle that I'll put on ice cream. He said, you got to think of every possibility, right? You want to exhaust the possibilities when you're trying to, really probe the utility of organic molecules in a program. Anyhow, I digress. Where was I? So here's the review of the reactions. Good news, you guys. You only learned 3 new reactions in this chapter, okay? And one of them isn't new, right? The only thing you learned here was the mechanism for Antimarkovnikov addition of HBr across a pi bond, of course, using peroxides. We talked about allylic bromination, wherein you use NBS and light. And then last is the bromination of an alkane, which is much more selective than chlorination. Chlorination is also a reaction that you learned in this chapter. However, it's just not used nearly as much as bromination. All right, there we go. Well, with all that in mind, I thought we would take some time now to do some practice. So let's find some Taylor Swift blank space here, and we'll give this the old college try. So 10.44 is a question, or some good questions in here. So let's look at 10.44a, and the question is simply, how would we go from here to here? And you have to provide the reagents for this. And that one's a pretty fast one. So I'm going to ask you, what if you wanted to do, come on, what if you wanted to do this? All right. There. So think about these 2 reactions. I'm just going to grab a drink of water and move my desk. right. Okay, so for our first reaction, my pencil, I think the best mode of attack here, since all CH bonds are equivalent, we can just use chlorine and light, right? And that we're only going to get one possible product. However, in the next one, we don't have any way to go directly from cyclopentane to iodocyclopentane. There's no way that we can do that. And so the best mode of attack that you could take here would be, I think, to make, if you made cyclopentane bromide or bromocyclopentane, you could take that and do an SN2 with sodium amide in a polar aprotic solvent like DMSO or acetone. And so then the question becomes, you know, how do I get here from here? And we know that we can do that simply by treating this with bromine and light. So a bromination followed by an SN2 reaction. Let's look at something that's a little more complex. What if I wanted to do this? If I wanted to take cyclopentane, and what if I wanted to make cyclopentanol? Okay, I want to take cyclopentane and make cyclopentanol. Could anybody suggest to me where I might start? If I wanted to take cyclopentane and make cyclopentanol? Well, I know it's hard to answer this type of question over Microsoft Teams. Oh, somebody's got an answer. Yeah, Patrick, you're absolutely right. So the reason that Patrick said we'll start with bromination is because if you have an alkane, okay, hear ye, look deep into my eyes and I'll hypnotize you. Whenever you have an alkane in organic chemistry 1 or organic chemistry 2, you've got one option. Okay, you learn one reaction that you will only ever use, and that is either to do bromination or chlorination. Now let's do bromination because bromine is a better leaving group than a chlorine. So we're going to use bromine and light, and we're going to make bromocyclopentane. Okay. Then what we could do is we could treat that with potassium T-butoxide in order to make cyclopentene, and then we could just do hydration with acid to make cyclopentanol. Now the reason why you use T-butoxide is you use this to suppress the SN2 reaction that would occur with sodium ethoxide. Okay, so you want to avoid that. All right, so that's the kind of rationale that you want to take, or the kind of approaches that you want to take to do these types of questions. Let's take a look at another one. Let's say I wanted to take cyclopentane, I'm kind of obsessed with cyclopentane, and you wanted to make trans 1,2-dibromo cyclopentane. So if you wanted to make this compound, I'll clean up my dash here. There. If you wanted to make this compound, plus it's an enantiomer, how would you do that? The same thing. If you had cyclopentene, right, as long as you have the alkene, you can take that and just treat it with bromine, right? Molecular bromine, not with light, because that's an allylic halogenation, right? So we don't want to do that. We're just treating it with bromine. We go through the bromonium ion. So how do we make cyclopentene? The same way we did before. We started with bromination, okay, radical bromination to make bromocyclopentane, like that, and then we use potassium T-butoxide to make cyclopentene. Okay, again, same kind of rationale. All right. With that in mind, I thought we would take some time and practice drawing some resonance structures. Resonance structures are something that students tend to struggle with from time to time. In chapter 10, when we look at radicals, usually by this point, students are quite confident in drawing resonance structures for carbocations and carbanions, but radicals can be a little tricky to get the hang of using the fishhook arrows. So I want to try a couple of them here. If you you know, don't need the help, you could maybe look at something that's more difficult, but for some students, these really pose a problem. So I'm going to go over a couple of them with you here. Okay, here we go. Okay, so let's start with 10.23a. How do you know that you can draw a resonance structure? Because we have an allylic radical, right? We have a double bond, and then we have a radical. That's an allylic radical. So what ends up happening when you draw a resonance structure is that basically you invert this kind of, right? The double bond ends up over here and the electron ends up over there, the unpaired electron. So somehow you're going to end up with this contributor, right? Where you're going to have the double bond here and the unpaired electron over there like that. So now you need to draw the fishhook arrows. Well, in order to make a bond, that pi bond, you have to have two electrons, right? There's two electrons in a bond. So where are you going to get the two electrons from? You're going to get one of the electrons from the radical. You plunk it there between the two carbons. The other one is going to come from the pi bond. You plop it right there, okay? And since you have both of those fishhooks meeting in between those two carbons, that denotes that you're going to form a pi bond there. So since there are two electrons in this pi bond, you can draw another fishhook arrow that shows the unpaired electron ending up on this carbon over here. And those are the two resonance contributors for this radical. All right, we want to use the exact same rationale here for B. Now here we have more resonance contributors that we can draw, but let's get started. We see we have an allylic radical right here. There's no way that you can draw a resonance contributor with this radical and this pi bond, starting with those. That's impossible. All right, so you start with what you've got. You've got this. So what are you going to do? You're going to end up swapping these positions, right? You end up putting the double bond here and the radical over here. Let's draw how we would do that. We're going to take this radical. We're going to plop it here. We're going to take one of the electrons out of that double bond, put it there. Then the other electron is going to go over here. We're going to draw a resonance arrow. We're going to draw the 5-membered ring. We draw the methyl group. Start with the stuff that hasn't been touched. Okay, none of this stuff that I have drawn here right now, none of this has been affected. But we have a double bond here, this exocyclic double bond now, and we have an unpaired electron. Can I draw another resonance contributor? That's my question to you. Can I draw another resonance contributor? Yes or no? Yeah, absolutely we can, right? How are we going to do that? Same thing. We're going to take this unpaired electron, put it here. We're going to take this one and put it here. And then we're going to move this one over here like that. And that gives us our final resonance contributor, which is going to look like this. We draw everything that remains untouched. We formed a new pi bond here, and we have an unpaired electron here. And that is the last resonance contributor. There are no more after this one. All right.